Hi everyone, and welcome to our channel. In this webinar session, we are just going to introduce the vast majority of the teams who are already using our inverters, inverter kits, or they are just planning to use probably, or even for some team members or potential customers who are planning to purchase our kits in the future. So we will cover several things during the session, mostly for the wirings and the installation-wise perspectives in terms of the mechanicals and the electrical-wise and some software aspects as well. My name is Csaba, and here is my colleague Richárd, who will also introduce the software-wise perspective and configuration-wise technical details for the inverters and the motors. So,
hi, I'm Richárd, and I'm head of the software development at Derating Innovation. And in the second part of this session, I will talk about a little bit about the motor control overview of our inverter. I will talk about the configuration, how to configure it. And lastly, I will talk about the setup procedures, the calibration procedures, how to spin the motor for the first time. So, and right now back to Csaba, and he will introduce you the physics of the inverter.
Yeah, first of all, I would like to introduce a little bit regarding the documentation hub that we have. So there is a website that we have called zdrive.eu, which collects all the information, all the basic information which might be necessary for the troubleshooting, the installation, and all the specs which might be interesting for the FC kit. There is a guidance technically which is informing you regarding the whole procedure of the setting up. There is a related document section here where you can find all the basic information, all the data sheets, all the specifications, all the application manuals, all the drawings, and so on. So all the basic information can be found here. We are not covering everything during this session because these are technical related aspects, and the raw values of the information can be found here. We are not focusing these specifics of this of the perspective of the installation via this webinar session, but we will just cover the basic principles of how to actually carry out the system. So first of this is the wiring. Actually, if you are heading to the wiring section, you will find pretty much information with the quick start of the kits. So once you are here, you will find some essential info regarding the inverters. First of all, you will find the face of the inverter with several connectors on board. You can see there are two inverters within one casing. We split it by half technically with L1, P1, and S1 of the unit. This means that there is a harness connector here, there is a sensor connector here, there is an AC connector here. In mirror, there is a other one for the other inverter inside, and the HV plus HV minus is common for the two inverters in one case. What I would like to mention here is the low voltage wiring wise perspectives, which might be considering that the connectors are pretty dense in terms of the attachments to the inverter. Therefore, the maximum cross-section of the wires is 28 AVG approximately, and maximum is 28 AVG could be used for this one. And this is like a hard requirement. If you are using a wider cable than that, you will face some issues with the crimpings, and then further issues with the connecting errors, and then contact errors could be present, so which should be avoided. Therefore, yeah, it's like a requirement to use a maximum 28 AVG. And additional information is that we recommend to use PTFE cables for these cable attachments. Is because of the robustness of the cables, the mechanical stability of the cables, and it's much thinner in terms of the insulation compared to the other kind of cables. So we recommend to use PTFE cables across the L1, the S1, and the L1 and the S2 connectors as well. So the L1 is the higher, the harness, low voltage wire harness connections. Of course, the L2 is one as well. So within this section, I mean this, you need to use this one for the wiring harness. And if you are using like another kind of motor compared to our motors, which is available, you should use this one for the sensor connections as well. If you are using our kits, like the whole kits, you can use the the standard wires that we are offering for the sensor cables, and that's it. So it's pretty straightforward. What you need to take care of additionally is using the right crimp tools for the attachments, because as I mentioned, it's pretty dense and the connections are pretty small in terms of the crimp sizes, and therefore it's very important to use the right tools for this one. There is a Molex one which should be used in this kind of operation. This is a specific kind of tool where you can attach the specific crimps. There is only one crimp type, I think, which is compatible with this tool. It's like a custom type where you can attach the crimps here. You close it and you just need to crimp it. There are various kind of AVGs could be compatible with this crimp tool, but this is an important tool to use whenever you are just making the harness. Also, an important tool is the insulation remover. This is a specific tool which also compatible with several kind of cross sections, but this should be used really for the manufacturing of the harness procedure. Okay, if we continue the guidance here, there is a section which also mentions the power supply requirements. It's a crucial part because we had a lot of information from the team members who had failure with the powering up of the inverters, and that's mostly due to the inappropriate power supplies. We require at least 2 amps of current rating per inverter, and by this I mean for each inverter modules within the case. So there are 2 inverters within one casing, so you need to have 2 plus 2 amps of current rating for each inverter block to maintain operability. This of course doesn't mean that you need the whole 4 amps of current rating during operation, but during a startup sequence you will need more current rating or current draw than a normal kind of operation. So this is why we require at least 2 amps per inverter. It's a requirement to operate stably. Otherwise, the power supplies within the controller unit will not start up properly, and it will just stuck in a boot or something else maybe. Some power supplies as well are facing issues. If you run into an overcurrent situation, it will flag an error state, and it will not exit from the error state unless you depower and repower it. So just make sure that you are using the right power supply with the right current ratings, and if it's there, you should be fine. Also keep in mind that with the position sensor attached, the power supply, the power draw will be more than just the standalone inverter by itself. So what you will be able to see on the laboratory power supply during operation is that if you attach the sensor, especially if it's a resolver, because it takes a little bit more than a conventional encoder, it will consume more, and that's normal. So that's fully normal for the operation. Probably that's it for the generic kind of ways of the power supply topic. Regarding the wiring, there is something a little bit more to mention here, which is the routing actually. I will show you the actual principle how to make it a little bit later, but I just mention here now that the plus and minus wires of the low voltage power supply should be routed as close as possible to each other. By that I mean you need to either like connect it with zip ties or something, or twist it a little bit to make like a fully connected or very close connection to each other to be robust and noise proof. Also information that you need to make sure that the inverter is capable of using 28 AVG wires, as I mentioned formerly. Then that means you need to provide a separate power supply for each inverter. You cannot like daisy chain or something else the connections. The best principle is to use like the star point topology for the groundings, and as dedicated wires for the positive wires of the low voltage power supplies. There are multiple positive connection points on the inverter. This specific quick start guide does not mention it, but there are multiple ones. So you can use more if you want to, but generally if you are just using these 2 pins here, it should be fine. So it should be okay. Okay. Regarding the CAN wiring as well, while we are just here with the low voltage wiring harness and so on, it's very important to make a proper CAN wiring. If you don't fire the rules, the thumb rules of the CAN wiring, you will face issues with the connections. You will face issues with like connectivity to the inverter in general. So it's very crucial part for the proper operation of the unit during the race time, if you are just controlling via VCU or even just like a bench test for using. The inverter is having two CAN buses on board. CAN 1 is meant for the basic setups, which Richard show you later, and the CAN 2 is meant for the runtime, the vehicle level installation. These shouldn't be connected to each other, so these should be kept aside from each other. And the CAN can be like if you are connecting all the inverters to the one CAN bus, you can do that, but keep the CAN 1 and CAN 2 separate. So you can have all the four, if you are using an all-wheel drive system, or all the two inverters in one CAN bus. Just keep in mind that you shouldn't mix technically the two CAN buses. Okay. And also there is one more important thing with the CAN bus. Is each inverters are capable of doing some CAN terminations here. I will show it later, as I mentioned on the benchmark. But so if you open up the lid of the inverter, it doesn't really actually. Yeah, it's here in the manual that if you are opening up the lid of the inverter, there are dip switches inside the inverters, and you can terminate the bus on whichever inverter you prefer. So, but only you should do it at once, of course, at the end of the bus. Or if it's not technically the end of the bus, it should be just one of this side of the CAN bus. The other side should be at the vehicle control unit or something else that you are using. I'm just willing to show you now how the principle is actually working in real life conditions. Just let me check it quickly. Okay, so here's the basic setup that we are having here. It's a bench test. It should be very similar that you should carry out actually. First of all, I would like to introduce the low voltage wires to you guys. So this is here, we are using PTFE wires. Just a second, maybe it's not. Okay, so here is the low voltage harness. Technically, we made as a mock-up here. This includes the power supplies and the CAN areas as well. Now we have just created the star point topology point here, which is the common ground for each inverters. And there is a CAN which is more like stubs at this moment, but the CAN should be routed like until this point here, where you are just making a connection. It's allowed to use slightly longer stubs with the CAN bus. I would say like it's 30 centimeters of stubs are just fine for the CAN 1 and CAN 2 interface if you are using that. And you should terminate the bus at one point of the inverters inside. So if you open up the inverter case, I just make it a little bit more zoomed here. Okay, so you can find the termination dip switches here. So you need to trigger those, and that's all for the CAN interface. So that's it. Make sure that only this part is openable and then usable from the customer side of the inverter. Any other parts shouldn't be opened or shouldn't be altered during operation. So you should keep in mind this. Okay, so let's continue with the low voltage harness. So there are dedicated wires for the power supplies here as well. So as I mentioned, here is the low voltage ground at this point. It's a common point here. Maybe I will show you with my phone if it's easier to introduce. As you can see here is the entry point for the low voltage ground, and there are separated wires for the positives for each sides of the inverter. So this should be in that way. We will also make some mentionings with the wirings and so on a little bit later, but that's for a second kind of iteration of the showcasing. So this is what you need to carry out with the low voltage wirings. Okay, the next principle should be the moving to the high voltage side of the inverters. Here you can find some basic information for the high voltage AC wiring in this manual here. So as I mentioned, on the faceplate of the inverter, there are two connections for the AC. These connectors are not IP rated and neither interlocked compatible connectors. We made it on purpose because of the size and dimension constraints of the inverter. It should be like an in-compartment kind of operation for the FSIC inverters. So the team should carry out some casings for the inverters, and so some kind of compartment which is necessary to put the inverters in. At this point, I would mention that it's very important to properly make the compartment, but we will also take a part here for the grounding kind of perspective here. It will be later on this session. So at this point, I would say that what you only need to take care with the inverter side of the AC cables is properly cream the wires, and that's all for this one. For the motor side, we will also take some information how to properly assemble it, but for now this is it technically. For the DC wiring, it's a little bit more tricky than that. So first of all, I would like to mention the actual carry-out wise of perspectives of this one. The inverter is capable of using some shoe terminals in terms of the attachment. Therefore, you need to take care of the positive locking due to the requirements of the former student standards. And this is a standard off-shelf kind of tab washers which you can find, and then you can buy it wherever, and you can use it. It makes the inverter rule compliant technically. Also needs to mention that the inverter does not include any kind of pre-charge system inside, neither discharge system. The inverter is capable of doing discharge by itself, but this is not really meant for an operational discharge. It should be like only for maintenance kind of discharge. It takes like 5 minutes to fully discharge the capacitance inside from the inverter. So this is not meant for like operational wise of discharging, but only for like maintenance wise. So fuses are also needed from external ways from the inverter. Some teams are using some separate kind of fuses for each inverter blocks, or you can use even one bigger one, but it should be like separated from each other. So each block should be having a separate fuse inside. During a procedure of the startup and bench tests, you can use a high voltage power supply, but during like a dyno kind of operation, it should be avoided. As mentioned here in the document, it shouldn't be used for dyno testing and so on. Only for basic spin-up testing like an encoder calibration and so on. So it should be avoided. If you are willing to use some dyno test or bench test at somewhat loading the inverter, you should be using like a battery instead, like a 48 volt battery or something. If you are using this, you need to take care of the limits settings of the inverter. So as I mentioned here, you need to adjust the voltage over voltage limits of the inverter. If you are using a 48 volt battery, you should use a 60 volt of over voltage setup for this one. And the most critical part, I think I would say regarding the installation, is the grounding of the whole system properly. We had a lot of queries, questions, and concerns from the team how to make it properly. Some teams had issues as well, how to make it fully noise proof and robust, the system by itself. If you are following the rules that we have set here, you should be fine with this. So I would say the very first thing here to introduce, as I mentioned, you should design your own compartment for the inverters. This is the 0 step technically. What you need to take care of is using a metal plate as a base plate for the inverter. This should be like the common ground point of your own vehicle. The vast majority of the vehicles in this kind of championships are composite vehicles, most likely from carbon fiber and so on. These are capable of transmitting electricity and power, but shouldn't be used as like a common ground and so on. We require our systems to have like a common ground plate for each inverters, and this should be like the common ground for the whole powertrain system of the vehicle that you are having. So you should enter here all the shieldings and groundings of the system, including the low voltage ground. So technically you connect the low voltage ground here to the common plate, and all the shieldings, all the groundings of the powertrain system should be connected here. And as well, if you are using some else devices like control units and so on, you should put these units to the common potential by this plate. So I will also show you around this specific plate that we had here as a mock-up, but you should use very similar kind of principle for your own applications. I think we can show this as well. So this could be like an important for with my phone. So this is a common plate that you are having, as you should have inside your compartment. And as I mentioned, formally this is the ground connection here, but there are multiple connections as well. So the inverter itself is connected to the common plate here by the screws. This is just fine. You should follow this as well. Of course, if you are using more inverters like an all-wheel drive kit, you can connect multiple inverters to the common plate here. But keep in mind that you also need to connect the sensor shielding here as well, the DC shields, DC wire shields as well, and even for the motors, it's not fully determined if you are just connecting your specific motor or the upright. By upright I mean this here, this installing, but you should connect this one as well to the very common point here, to the common plate of the inverter. This is a crucial part because unless you cannot use the AC shields as for the groundings, this should be using like at least 4 square millimeters of wire for each uprights of the vehicle that you are having to the common plate here. This could be through a connection, of course. You can use like an in-between connection for the compartment, but it should be like this. So it's very crucial part, just again, to have all the wiring connections, all the shieldings of the wirings connected to the common plate here to make a proper equipotential bonding and so on with this. So we are also using in this principle some virtual electronic kind of connectors here. This should be both off-shelf, so it's very simple and relatively cheap as well to make a proper connection to the groundings. This makes this system technically fully working and like a proper one, so I wouldn't avoid using this at any points. Okay. I think we have went through all the parts of the groundings and the electrical wires. Some parts are still remaining for the electricals, but we are just continuing for the mechanical kind of integration, and that would involve some topics to the electricals as well. So I would move to the sensor cable a little bit, and I would like to talk a little bit more regarding the sensor cable. This is also a very important part of the system, because the controllers are introducing like a closed loop operation, and your only feedback from the motors at the position sensors. In this case, we are using resolvers with our motors, and we are using shielded wires, of course. What you need to take care of properly is I will be able to show this, but just to give me a second. So this is what you should expect with a assembled motor in your upright, most likely, without, of course, the cooling jacket and so on. But this is the basic part of the system. This is the position sensor cable here, and this is a critical part of the system. So most teams are having issues with these kind of cables because of the improper installation. The proper installation of the cables would be to properly mount the wires to the system. To the vehicle by rigidly, and the only part which should be moving is like a maintenance loop at closely somewhere close to the moving part of the system here, and this should be follow the guidance of the cable manufacturer, which is here could be either T connectivity or Amphenol, so it should be like T connectivity or Amphenol. What you need to take care of is the bending radius and the ruling of the former student rules, of course, which lengths of the cables can you have freely moving and close to the upright parts from the system. So this is important thing here. We also made a test bench where we are just made some fatigue tests with the cables around, and we found out that there is an improved kind of cable compared to our previously offered ones, which was Amphenol, and we are now offering like a TE connectivity cable with our new orders and new inverters and new kits, and we are able to provide this to the teams as well. If you need this, just feel free to get back to us, and we will just offer you. So, and for those team members who are using the Amphenol cables still, we have worked out like a document for this one. If you are hitting up the documentation hub here, and you are moving downwards to the position sensor connector assembly here, there is a strain relief that we have created, and we are recommending the teams to carry out whenever they are just using the Amphenol cables. This extends the lifetime and the cycle times of the cables pretty much. So if you have these cables and haven't done a strain relief yet, we would highly recommend to use this one, at least for the cables that they are having, not to have any issues during events. Or even better, if you are just getting back to us, and we will offer you the upgraded one, which has dramatically more cycle counts than the Amphenol ones. So this is what we recommend. Okay. If we are here with the motor showcasing, I would like to show you a little bit more regarding the interlock wires. So there is an interlock loop inside the motor. You shouldn't. It's not a must to use this point for the interlock connection. This is just like a loophole for the interlocks on the motor side. If you are just routing this wire through the inverter, the motor's casing, you should be able to create like a loop here and make it in this way. If you are attaching like a wire-to-wire cable, a connector here, you can remove it safely from the system, so that's completely fine. Some teams have made it fully like connected to the system. We wouldn't recommend this because then you cannot detach the cap from the system at some point. So we would recommend to use like a wire-to-wire connection here. Okay, if you are just moving to the servicing of the motors, we also had quite a lot of topics here to discuss regarding how to properly service the motors, and how to dismantle and reassemble the motors without damaging the system by itself. So I will just show you quickly how to properly dismantle and reattach the parts from the system. So what you need to do first of all, when the motor is still in the vehicle, you should be able to clean the AC cables from any derbies, any dirt, any dust, anything else, because you need to slide the cap of the unit. So once it's done, now it's clean, so I don't need to clean it, but this should be the first step to properly clean the AC cable so not to have any kind of dirts and derbies in it. Once it's done, you should detach the position sensor connector, first of all. I will just quickly do that. And once it's done, what you need to do first of all, is to disconnect undo the bolt from the position sensor, because if you don't do that and you just start removing the cap, it could be damaged. And once the PCB is damaged, it's not so fun to repair. We wouldn't even recommend to repair it. We can offer it as a spare part for the motors, but I would avoid using that. So first of all, you should need to undo this bolt here. The second thing that you need to do is to do some silicone spray here, just a simple silicone spray that we are using here, just to lube up a little bit the wire prior attaching. Now you can undo all the bolts here on the motor side. So if you are undoing all the bolts here, now then you can slide the cap upwards. Just keep in mind that this position sensor connector should be avoided from any kind of damages. And once you are lifted up here, you can just move it quickly, and you have the parts here. So the next thing that you need to do is to untighten these bolts here, because these are locking the wire, the AC wire inside. and then you will be able to freely undo these bolts, and the AC bolts can be undone. And once they are undone, you can fully remove this AC wire, and you will be able to service the motor. If you want to make like a mechanical service and remove, for example, from the upright, I would highly recommend to reattach the cap backwards to the motor, because then you are not damaging the PCBs and so on. So if you are continuing the dismantling the procedure by removing the motor from the upright for any reasons, keep in mind to put the cap backwards with the very same procedure. So you redo the AC bolts, you redo the tightening bolts here, then you reattach the cap. Do not forget to re-add some lube for the AC, because of the O-rings could be damaged otherwise inside the end cap. So it's very highly anticipated if you could lube up a little bit the AC wire here. Then you can just pull it backwards to the cap by safely having the sensor connector here. Then you can redo the bolt here somewhat, and that's all. That's all you need to do for the servicing. Here, I would also like to mention that for the positive locking, the tab washers are not necessary for the AC connections, because the cap of the motor is designed in a mindset that it doesn't let the bolts fully undoing it themselves if they are loosening up. So you don't need to do some positive locking here. This is by design guaranteed. It's working as expected. Okay, so when installing the system backwards, I will just show you something else quickly. You need to really make sure that you do not damage the connections here. So the most critical part is the sensor connector, which could be breaking, and that's unfortunate, because just gluing them backwards is not enough for a proper connection. You should report back to us if you have such an unfortunate event, and we will just provide you a quotation for a replacement PCB. By talking the PCB and the replacement parts here, we are also offering some other kind of replacement parts which are available for the motors. So of course, if the end cap is damaged, we can provide it as well. The PCB can be bought as a separate part, of course, because we had a lot of queries from teams who had this as an issue, and we developed like a whole maintenance kit for the motors. This includes all the sealings, all the O-rings, all the shaft seals, and all the bolts for the end caps for the motor. This is a recommended part. If you don't properly tie the bolts on the motor end caps, the tiny O-rings will just perish during the session, and it's a very necessary part for a proper like a sealing of the end cap of the motor. So then, if you are having issues with any kind of seals, I would highly recommend to use like a maintenance kit as a replacement, and use the new seals for the motors. By this, I would also like to mention that it's very important to use like a proper tightening torques across all the tightenings, so for the motor bolts. If you don't properly follow the guidance, as I mentioned, you can perish the O-rings on the end caps, and in a worst case situation, you can even damage the AC connection. Technically, it's a PCB here, which consists like connectors for the both connectors, and you can just damage it if you are not properly following the guidance on the torque sections. So it's very important to read across the application manual and check the torque specs of the motor. As I mentioned, if anything breaks, just don't try to hack around. I would highly recommend to get back to us as soon as possible if you have anything broken, and we will offer you like a replacement parts. For example, as a maintenance kit, or if it's more like a custom kind of issue that you're having, we are also open for discussion for this one as well. So we are just helping out each team members if any issue happens. So I will just put it a little bit backwards together. Some lubricant still remain here, so I will just relube it now. Okay, it's just enough here. So what you need to also take care of is the motor mechanical parts of the system. So when you are starting a dyno test of the motor, I will just show you around with my phone. There is the shaft seal here. It's a crucial part of the motor, and it's prone to be damaging if you are not using properly the system. So whenever you are just doing a bench test or a dyno test, make sure that you are properly lubricating this during the sessions, because otherwise it could be damaged, and worst case situation you can even damage the shaft itself. So it's a critical part to properly lube up if you are using it as a test bench or so. If you are designing your own gearbox, I would highly anticipate, it's very recommended and it's a must to properly lube this kind of this seal during the sessions. So do not make like a face here which prohibits the lube at this section. So it's an important part to lube up properly. As I mentioned, otherwise you could even damage the shaft, which is pretty much unrepairable. So that's very unfortunate if it happens. So make sure everything is fine. If you are here with the end of the motor, there are also some mentioning here regarding the loads with the shaft and the axial forces. So within the motor, there are two bearings which should be like kind of delicate in terms of the axial forces. So it's in the manual which are the actual parameters here which you need to take care of, but it's limited. And you should be like considering the actual forces that you can apply maximum in an axial force here, not to damage the motor by itself. Also, when you are designing the counterpart here, you should really make sure that the sizes, the dimensions are properly met according to our requirements, which is here in the documentation hub. If you hit up the F-mode drawing here. Just a second. Okay, it's here. So all the specs can be found here for the shaft counterparts, and we even designed like a model for the hollow shaft parts and the counterparts that you should design technically. We uploaded this to our documentation hub. You can find it here. You can print it for testing, for example, and so on. So you can find the model online and upload it. So that's pretty straightforward for reference checking, I think. Okay. Just this. Okay. The next thing should be like the cooling perspectives of the system that you need to check. I will just show you around how a motor looks like from the inside with my phone, most likely, because it's more clear to see. So what you can see here is like the stator of the motor. It's like an epoxy coating of the windings here inside, and this is technically the spot where all the heat will generate inside the motor, and it will just push it through to the casing. If you can, now we can see it from the upwards. So all the heat will generate here, and you should remove the heat technically from this kind of section during the operation. I will give you a little bit more. Okay. So from the internal structure, there is the skirt which transfers the heat outside to the unit, and you should design your own cooling jacket to transfer and remove the heat from the motor. We would highly recommend to exclude the coolant from the welding spots here. So I would keep all the sealed zones in between the two welding zones here. So the recommended solution for the connections is the O-ring kind of sealing with your jacket here. And in order to make a proper kind of sealing in between in the coating of the motor and your cooling jacket, is having the motor as clean as possible. We have seen some motors pretty much damaged during some kind of testing procedures or and so on, and making some deeper scratches on the surface of the motor is not recommended, because the sealing will be just reduced. The sealing forces will be reduced, and the gaps that you are creating with the scratching could cause issues, and like the sealing shouldn't be just as expected, and those will fail to properly seal. Okay, the whole cooling of the motor can be very common with the controllers. So you can use the very common cooling system with the inverter that you are introducing in the system. So you should expect like the common kind of flow rates and the pressures, and so they are just compatible with each other. You should design your own cooling jacket in a mindset. It should be like that. Okay, so the next thing should be like, while we are with the cooling nodes here, I'm just putting back the bench here, and then just having a few words with the inverter cooling. Yeah. And also I will just show you with my camera, I think. So on the inverter side, there is a 3D printed cooling plate from the inside, which ends in two Festo high temperature connections here. This shouldn't be undone because these are glued inside the cooling plate. And if you are undoing these, unfortunately, you need to send the inverters back to a service, because we cannot make sure anymore that the sealing will be proper, and we cannot allow any kind of possibility for leaking inside the high voltage system, because the high voltage system is not a game, and any kind of leaking should be avoided and must be avoided. So undoing these Festo connections are prohibited, even though they are not necessary to alter or change, because there are multiple kind of connections available with these kind of Festo connections. If you are checking the Festo when you are here, there are multiple kind of angles like elbows, reducers, enlargers, and so on available on the market. So I would highly anticipate if you could use some of these ones. You are fully rule compliant with this kind of connectors. Just make sure that you are choosing the high temperature series of the Festo connections, because otherwise you could face some issues with the scrutineering and so on. So yeah, keep in mind that you are using the proper Festo series in this one. So in general, I would say we have covered all the basic principles, what to take care of and what to look at when you are just making a basic setup for the inverters and for the motors as well, especially for the grounding, because this is a very crucial part for the system. If anything arises in terms of the questions during the session, please feel free to ask. If you have any other questions that you want to ask, you can ask it via emails after the session. But this webinar will be available after the session here, so you can replay it whenever you wish to, and you will see the basic principles, what we have done here. We are also taking photos afterwards, so we will create a formalized document of this afterwards, so you will be able to see it in a formalized way in this kind. So that's all for the mechanicals and the electrical ways. My colleague Richard will continue with the software kind of setting up and configuration. Thank you very much.
Thanks, Csaba. Now you are familiar with the wirings and mechanicals, and let's continue with the software and configuration. I'm continuing with the documentation hub Csaba already showed you. Here I divided this part into three sections. We will cover the motor control overview, we will cover the configuration and the setup procedures. Let's start with the motor control overview to see how the inverter works in the basics. Here you can see the block diagram of our inverters. We are using a state-of-the-art field-oriented control, and we have proprietary algorithms which increase the motor control quality, you can see here. And also, of course, the motor control part is much more complex, but here I'm just showing you a simplification and have a rough understanding how the system looks like. I would highlight the current controllers, which are located here. We have two current controllers. One is for the IQ current and one is for the ID current. And both current controllers are very important to work correctly or properly, because these are responsible for torque production, and even more in magnetic field weakening region, it opposes the back EMF effect of the motor to reach higher speeds at the end of the speed region. So the current controls has to be tuned properly, but this tuning in the case of the DTI inverters is not necessary, because the PI current controller gains are computed automatically by the inverter firmware based on the LD and LQ parameters, so Q inductance and D inductance. And furthermore, we did extensive testing in our dyno with these parameters, so you don't have to, so you can trust these parameters and you don't have to validate these parameters. You can just use it, and the current controller should work fine if the assembly or the whole system is correctly assembled. The next thing is, in correlation with the current controllers, is the MTPA, the maximum torque per ampere, and field weakening regions. Our inverters are receiving AC current vector length targets, so AC current targets basically, and we are distributing these AC current targets into IQ reference and ID reference ourselves in the inverters. You can see this part here, I show you here, and this block distributes the IQ or calculates the IQ reference and the ID reference, which goes into the current controllers. So you don't have to calculate it, because our inverter just do it itself. The maximum torque per ampere algorithm has effect in the until the base speed. Until we are reaching the base speed in the base speed region, and when we are reached the end of the base speed region and we are entering the field weakening region, we are activating the field weakening algorithm, which is basically a PI current controller. Let's back a little bit to the MTPA. So when we are below base speed, the MTPA algorithm calculates according to the IC current reference how much ID current must be injected into the motor to have the best torque performance for 1 amp of current. But this only works until the end of the base speed, and when we are reaching the end of the base speed, there is a PI current controller which actively driven by the voltage vector length of the motor. This means when the motor starts to approach or goes above the base speed, the voltage vector will be higher, and the PI current controller will inject more ID current in negative to oppose the back EMF effect of the motor, thus increasing the RPM above the base speed and entering the constant torque region of the motor, a constant power region of the motor. And that's how the MTPA and field weakening and vector distribution works in our system. And we will talk about later in the setup procedures, but firstly, we always recommend to do the first pin without the MTPA and magnetic field weakening to test if the essentials, the position sensor and everything works fine, and then enabling this algorithm to have the best performance for you. The next one is the limiting and ramp control. We have a fault and limit system. The fault system is a system which helps to to avoid damages in the system. So there are conditions like over voltage, under voltage, gate driver error, absolute overcurrent, and so on. When you have to stop the operation immediately because something crucial, something critical happened, and you would like to stop and have the motor coasting and restart the system when it's over or when the condition is not active anymore. This is restored automatically by the fault stop time parameter, which can be set, and this can be determined by you. So you can set it to 100 milliseconds if it's suits for you, or you can set it to 5 seconds also. And this fault stop timer starts to count down when the condition is cleared. So, for example, if the overvoltage condition is not active anymore, then it starts to count down and recovers into a no fault condition, and you can continue the operation. So fault stopping the modulation immediately because it's estimates or assumes some critical issue. And we have limits, which are basically protections to enter the damage zone. It means that we're reducing the power because there is no critical condition yet, but we would like to avoid to enter the critical condition zone. So we will just reduce the AC current. The limit system basically modifying the AC current target sent by the source selector and thus from your system. And this is to prevent any further damage. We have input voltage limits, we have semiconductor case temperature, junction temperature, motor temperature, RPM, capacitor, DC current, and so on limits. And these limits are working a very simple method. Here you can see a graph about if you set the input DC voltage limit to start at 200 volts and end at 100 volts, it will linearly reduces the available AC current on the output, thus cutting or truncating your command according to this graph. And here, if the motor current max would be 100 amp, then it would linearly reduces at 150 volts, you already has 50 amp of current, and thus linearly reduces. When it reaches the 100 volts, it allows 0 amp of output to the inverter, thus preventing any further damage. You can monitor each limit via the graphical user interface and via the PC software, and here is the input voltage, case temperature, motor temperature, everything. And when this shows 0, it means it's 0 performance degradation is there. When it's 100%, then it's limiting your AC current or truncating your AC current 100%, so that's not allowing any more control in the system. Okay, so that's about the theory, about how the inverter works. And the next section is the configuration. Here you can see that every parameters are well described and provided here. So if you would like to have more information about a specific parameter, you can check here. I would go into let's start from the beginning, in the GUI, in the PC software, and show you how to use it, or just get to know the user interface itself. So when you start it, you have to select the serial port you would like to use or which is your diagnostic tool. You can check it in the device manager if you want. You can just keep the baud rate at this default settings and click to connect, then click to the available nodes. Right now, if you have a correct wiring, the nodes should show up here, and you can have multiple nodes on one canvas, and both or all of the nodes should show up here without any issue. And each node has to have a unique identification number, which can be set via the configuration tool. Click to the node, and right now you can see the dashboard. Basically, on the left side we have the menu. We have here the basic informations. Firstly, here are some real-time graphs, and here are the quick real-time graphs here. We have a right button to send the configuration to the inverter, set the parameter advanced or simples you would like to see, and this green notification just provides you if the inverter is enabled or disabled. And this basically just shows you that the inverter is online and ready for the communication. I will go from top to the bottom, and we'll go through some menus. Here there is the terminal. I will show you later, but this is used for additional troubleshooting when you are looking for some problem and you would like to have additional information which are not available here. We have the data analysis section, where you are able to observe and monitor the inverter parameters, current, temperature, RPM, and the field-related control D and Q current outputs. We have the sampling. The sampling is a function which allows you to capture real-time data into the inverter's memory, and this data is sampled at the PWM frequency of the inverter, so it has really lots of information involved. And in the passive sampling, you are able to capture data right now, or when the motor starts, or at a specific trigger events you want. And when this happens, you can download it from the inverter into the PC software, and you can open it by clicking to this file, and you can see what's happening here. I will show you in detail later. We have active sampling, which also do capture data into the memory, but also injects current into the current controllers, so you can observe how the system behaves when you have a step response injection, and you can observe how the current controllers are working, and you can verify them if they are okay or not. We have the limits I have talked earlier. You can observe if any parameter limiting your performance. So if you are feeling that you do not have the full performance out of your motors, you have to check firstly here if any limits hitting. If any limit hits, then you have to resolve to remove that limit by cooling down the inverter or applying more voltage and so on. We have a fault history, which means that we have the fault codes from the past, and we can observe a freeze frame data that when the fault occurred, but were the actual values of some variables, which helps you in troubleshooting. Motor parameters, these are the most crucial parameters here. The LQ and LD inductance is responsible for computing the PI current controller gains, and these parameters right now, the parameters of the DTI F motors, and they are validated and tested in our dyno. Also the phase resistance, fluctuating nominal motor voltage. At the default, you will get these data right, and you can use it and trust them. If you are using a custom motor, you have to type the motor parameters also here, but you have to validate, because you might it can be differences between the real life inductance and the theory inductance you get out of the simulation software and so on, and you have to type in and validate and verify the current control performance if you are doing such a custom motor development or you are using another motor. Also true for the flux linkage, phase resistance, and nominal motor voltage and so on. You have to validate always, because if you're not validating, you do not know if your motor working well or do you need to do some improvements and so on. The next is the rotor position sensor. By default, the DTI mod uses resolvers, but also we do support RLS LM44 interface. We also do support Heidenhain encoders for AMK motors, and also we have support generic third-party encoders with ABI interface. Here is 3 parameters: the encoder offset, the ratio, and if the encoder inverted parameter. These are very critical in terms of motor control, and these 3 parameters must be correct in order to have the best performance out of the motor. If these are not correct, you may have performance degradation, or your motor may not spin at all. And we have the encoder nonlinearity tab here, which we'll get back later. We have the control settings, where there are lots of settings here. I will not go into detail for everything, but these are the advanced menu here. These are the simplified menu. So if you do not have a specific reason to modify the advanced menu, then do not do it. If you do, you know what you are doing, then you can enable the advanced menu, and you can adjust these parameters. At default, for this time, it should work fine. This invert motor direction is important when you have calibrated the motor. Then you have to invert the motor direction if it's not turning in the good direction for you, like forward or backwards. The limit parameters tab. Here are the most critical parameters. Let's start with the motor current max. The motor current max is the parameter which is the maximum current that the inverter will ever output into the motor. So this basically gives you how much torque or performance you may have. You can set it to 10, and you can also set it to 120 maximum. The higher is this number, the higher torque you have, thus higher performance. What is very important here is that the motor current max and also any other AC current related parameters are understood in peak dimensions, which ampere peaks, and not RMS currents. So it means that it identifies the sinus peak, the amplitude of the sine, and not the RMS value. So if you have so you have to type AP key, because if you type RMS, then you have approximately 29% lower value than the peak. So just be careful about that. We have the absolute maximum current here, which is a protection, a fault protection. If the current controllers are mistuned, or there is any fault or something which causes that the current in the motor are higher than this number, then the inverter will stop the modulation, the PWM modulation, immediately. We have DC current limit here. You can enable or disable it, and you can type here how much is the maximum DC current you want to input your inverter. This is a PI current controller, and this is the KP and KI value, and you can change it if you feel some oscillations or transients. These are the DC voltage limit, which I also talked about a little bit. We have the DC voltage fault, and the inverter will immediately stop the operation when it hits that limit, and thus this limit must be lower than the voltage limit end in order to perform perfectly. And also the same true for the maximum input voltage. Here we have RPM limits. You have to limit the RPM due to to avoid mechanical issues. So here we did the testing at 88,000 RPM, and that was our limit here. But you have to put here, firstly, when you do the first testing, maybe a little bit lower value, but slowly you can increase to your design maximum RPM. Here we have the power limit, which is in direct correlation with the DC current limit, because the power limit is calculated. So from the power limit we calculate the DC current, and that DC current limit will provide you keep the DC current, which provides you this power on the input. And we have the temperature cutoff values here. These are limits, so it starts the limitation at 90 Celsius degree, and when it hits the 120 Celsius degree on the controller temp side, it will just give you 0 amp of AC current, and the same true for the motor temperature. Here we have the speed control and the position control also, but these are not relevant, I guess, for the formal student competitions. We have here the general settings. You can type a unique device name for the device, like front left, front right, and so on. We have the control source, so you can select the CAN1 and the CAN2 control source. The CAN1 is basically means that you can give commands to the inverter via the PC software. The CAN2 is means that you can command the inverter via the CAN2 interface, like from your VCU, or if you have a USB CAN adapter from the PC. We have the timeout parameter. If the controller does not receive a command in this time frame, then after it counts down, it will just stop the operation with the specified current, break current, which is 0. So right now it's 0 amp, but if we increase it to 10, it will just slows down the inverter, the motor with this current. We have digital I/O input and output. You can select which function you would like to assign to them. And we have CAN menu, where you can also set the controller ID, the unique node ID. This is the unique node ID, and you can set the speed and also the CAN map version, and also you can enable the CAN2 interface and enable the messages at the specific broadcast rate you want. And if you change anything, then you can press the right button, and it will just send the configuration to the inverter, and then it takes effect immediately. There are some exceptions, but most of the parameters takes effect immediately after you write the configuration. Okay, that's all about the configuration, and let's go to the setup procedures. So you have wired up the HV, you have wired up the LV, you have wired up the motor and the position sensor, and you would like to spin the motor, and this guide will go through, and we will go through that guide, which we will step by step go through the setup and calibration procedures which is necessary before the first spin. These are the prerequisites, and motor manually have to insert phase cables, connected, position sensor, and so on must be correct. Motor parameters configured, limit parameters, so you have to type your system input voltage limits, start and end correctly. Disable the DC current limit and set the MFV mode to none. I will do that right now. Because it's not done yet. The write operation is finished when it says config saved. And let's go to the next one. CAN2 setup. There will be a procedure, the closed loop step response, when we do need the CAN2 commanding source. So if we click here, you can see a step-by-step guide how to enable the CAN2 interface and how to start with that. You have to wire up your VCU, so you have to modify these parameters you can find in the CAN tab here. And also you have to wire up your VCU or your PC software or PCAN adapter, whatever you would like to use for the first commissioning. And then you have to configure the commands, and when you have configured the commands and sending the command, you are able to observe these commands input into the inverter. So you press the terminal, CAN2, you select the CAN2 values, repeating, press the play button, and you can see here in real time what the inverter receives via the CAN2 interface. And right now I have a device here which is configured for sending relative current in percentage to the inverter, and I have here the cursor, and you can see here that if I have a potentiometer and if I increase the potentiometer to 100%, then it's basically ends at 100%. So the first crucial part is when you are sending commands at the first time, you have to make sure that you have encoded in the right format and the inverter decodes in the right format. And this terminal panel is a really good help for that, to monitor and observe what is the received current and if received command and really does that command is the command you have sent from your device. So I would recommend to do that for the first time, and if you are confident enough, or you have verified that your command in the whole range are correct and the inverter decodes it correctly, then you can move forward in the setup procedures for the next. Here is a graph about a simple algorithm how to do the first spin. Firstly, we have configured the parameters. We have did that because we are using the default parameters. First one is verifying the rotor position sensor if it operates correctly without controlling the motor, just statically. Then we are doing open loop step responses. We analyzing the response and adjust the motor parameters if necessary, and do this loop until you get a validated current controller. Then the next step is the encoder offset calibration. This is very important. And when we have did that, also we verify the parameters, and when it's verified, then we go to the next one is the initial slow rotation. Then we give a little bit of command to the motor to spin a little bit, but not too fast, but just to see that everything is on the right track. Next one is the closed loop step response. It means that we will spin the motor from an external source. We are commanding via CAN2 interface. We are giving some target like 5 amp or 10 amp, and we will do an active sampling, like injecting 10 amps, and we will observe the output to see if the current controller performs well when the motor is spinning. And when we are done that and verified, the next one is the encoder nonlinearity calibration. Then if it's calibrated, then we go to enable the MTPA, and when the MTPA enabled, then we can rotate a motor even with a small load, and we are observing the control quality with passive samplings. We are looking for faults, noises, where noises and integrate and resolve if necessary. We ramp up to 2/3 of the base speed, and we are looking for kernel stability issues and so on. When the MTPA works fine, we can enable additionally the magnetic field weakening, and we increase the RPMs into the field weakening region with some desired steps, step by step, not just go fully to the max RPM. We are do 2 or 3 steps and analyzing before we go to the max RPM, and then we are complete the setup. Okay, let's start with verifying the rotor position sensor. So here the verifying means that we are connecting the resolver and the motor, of course, and we go to the rotor position, and here in the rotor position section you can see here this circle, and this circle basically represents the angle of the position sensor real time. And right now in this step we would like to identify some wiring and this kind of issues. So right now, give me a second, and I will move by hand the motor shafts with some strange noise. We have a gearbox here, and it's and you can see here that the circle is moved when I move by hand, and also you can observe in graphs also the A, B, and index graphs, and also real time how the angle, this is degrees, and how the angle changed when I moved the motor. The theory here is that you mark the rotor shafts, you move the rotor shafts exactly 1 rotation, and you observe if you get exactly 1 rotation also in the real-time graph, because it means that 1 rotation in mechanically means 1 rotation in the inverter and firmware, it's in synchronized, and that's what we would like to see. If we do not see that here, then we have to verify the cables, and we have to resolve the issue. The position sensor is the most critical, next to the current control, but it's the position sensing, it's also a critical issue, so you have to take care of it. Okay, when we have verified the position sensor, the next thing is to observe the current controller behavior. This procedure has to be executed when you are working with an unknown motor with an unverified parameters. The DTI motor is tested in our dyno, and it means that these motor parameters can be motor parameters are validated. So in normal procedure, you do not need to repeat this section for every DTI mod unit. I'm showing you this section to understand and learn how to find or verify the current controller, or find issues, troubleshooting when you observe some problem. And when you are using or working with an unknown motor, you have to execute this because the motor datasheet parameters may differ from the actual values, manufacturing tolerances, magnetic saturation, and so on. So that's why you have to observe what's happening here. We will execute an open loop and a closed loop procedure. The open loop procedure means that we inject step response without position sensor feedback, and the motor will remain stationary. This not requires encoder offset calibration, so we can execute it right now to see electrically how the current controller works. Let's see what we have to do. Firstly, we have to have no active faults, and we have a fault, of course, because we do not have voltage applied, but you have to have no active limits, motor parameters configured, enable signal. I have an enable signal configured and it's enabled, that's fine. In control settings, I have to disable the reference ramp enable, and I have to set the magnetic field weakening mode to none and control source to CAN 1. I write the configuration and I enable the high voltage system right now. Until then, okay, I have 550 volts applied to the inverter, and right now I do the active sampling and I write the configuration again. When you click the open loop, you can see that we captured a sample. You click the download button and in 10 seconds or something like that, the sample file should show up here. You click to that and it opens up. In this software, you can observe the real-time data of the inverter. Here you can see the phase currents with the blue and the red, and the total vector length, the total current vector length indicated with orange. Here you can see the IQ reference and IQ actual target and reference. Here you can see the actual ID current and the target, and here are the VD and VQ voltages. As you can see, we have injected step responses, and we can observe that the actual IQ value really well follows the target. So in this case, we can say that okay, the current controller performs very well. If you see that the actual value goes above the target or below, then you have to make adjustment in the motor parameters with increasing it or decrease. It depends on it's too fast or too slow. And let's say that it's validated. The next thing we have to do is not the closed loop step, is the encoder offset calibration. We know that electrically the current controller works fine, so it is safe to calibrate the encoders. Right now it's resolvers, because we need the encoder offset for the motor control algorithm. We have an automatic calibration procedure, so you have to type 10 or 20 amp of current, really enough for the DTI F mode. Press the start button, and the calibration procedure starts. Here you can see a progress bar, and here you can see that the circle is moving, and right now the inverter determines what is the encoder ratio, basically the motor pole numbers. So this encoder ratio indicates the motor pole numbers. The encoder offset must be a 0 to 359 degree value, and we have to have an encoder inverted, which is a true or false here. When the calibration procedure is finished, then you will get here the values, the degree, the ratio, and inverted, you can press this check mark here, and this just copy the parameters here, and you have to press the right button. I do not write here because I have good parameters also here. You can read the last calibration parameters here if some way you have closed, unfortunately, the PC socket or something like that. Later you can download it. Okay, so right now we have calibrated the encoders. We know that the current control works fine. Also, there is a calibration prerequisites before the encoder calibration. And the encoder ratio is 4. This motor has 4 poles, so it's quite good. This number cannot be validated, basically. Just you can make sure that if you execute it 3 or 4 times, you get the same value, and also the encoder inverted is also a given value. So right now we are able to give some command to the inverter. We have selected control source to CAN 1. So right now, if I do manual control here, then I'm able to control the motor with this, and we can see that the motor turning and controlling the inverter controls works fine. Okay, good. Next thing we have to do is right now the encoder nonlinearity calibration. Why it is necessary? This is necessary because the position sensor, the rotor position sensor contains periodic systematic error, and it can be mechanical, can be magnetic or signal processing nature. So you have to do it to decrease the torque ripple, decrease the DC and AC current ripple, and in that way you can increase the motor control quality of your system. Right now you can do that here. We do not have any applied curve here, and I will just set the control source to CAN 2. Sorry, closed loop step response. I will show you that earlier before going to that one. So before the encoder nonlinearity calibration, we can do the closed loop active sampling, and with the help of this feature, we are able to observe how the current control behaves when the motor is turning, because when the motor is turning, it generates voltage, and the current controller is under more pressure. So we have to observe what's happening when it's under pressure. So also you can do it also with higher RPM. You click to the closed loop and download the sample data, and you can observe also the injected step responses here, and we can also see that it's very similar to the previous open loop operation, but it can be interesting when you increase the RPMs. You have to also check the validity there. Okay, so let's back to the encoder nonlinearity. I will show you how much you can improve with this. So I will go to some RPM, let's say 7000 RPM right now. I click to the Now button and download the sample. The thing here is that it must be a stabilized RPM. So you have to have a slightly stabilized RPM, because if the RPM is changing, it can lead to nonlinearity curve deformities, which is avoidable. So right now we can see here that we have this kind of, not oscillations, but these waveforms here, and we can decrease it with the rotor position, with the encoder nonlinearity calibration. So here you have to select the sample you have downloaded earlier. You press the load configuration, and then we can observe how much it reduces the ripples. These waveforms, these periodic waveforms you have seen earlier, the purple one, these are directly related to the torque. So if you see oscillations on the purple line in the IQ current, then your torque is also oscillating with that kind of amplitude. And right now you can see here that we still have some oscillations, but it is because the MTPA is not enabled yet, but it reduced because this is 3 amp and this is 2 amp, and we have reduced this ripple a little bit more comparing to the earlier one. Here you can see it has also in the voltages, and also you can see that from 2 amps to 3.5 amps is the amplitude, and the U1 is much slower in amplitude, and this reduces the torque ripple and increases the motor control quality. So don't forget to do the encoder nonlinearity calibration because it helps a lot. And when we have did that and we know the current controls, everything is fine, we can go to enable the MTPA. We can do it in here. We can do only the MTPA right now. I just apply some brake here. So I applied some negative torque in the dyno to have a little bit of more ID to see how the MTPA operates, and I also took a sample, and right now we observe what it does exactly. So as you can see, here are the phase waveforms. The orange is basically the current vector length, and also we can see some periodic signal here, but the amplitude is much less, so it's basically 24.6 to 25.4, so less than 1 amp of current ripple can be seen here, but the current vector length here is basically very nice and consistent, so these waveforms can be considered as good. Also the voltages here, it's very nice, so this is kind of good operation. It can be expressed that this is a good operation for this. And right now the next thing is you can do a higher RPM test also with the MTPA, and when it's verified and you can say that it works fine, you can enable the magnetic field weakening by selecting this MTPA MFV mode, and write the configuration. and I will increase. So as you can see, we are here at the field weakening region right now. I can increase the RPM and I can stop it. And I took a sample to observe what's happening. I would recommend to go up to like 15,000 RPM, 17,000 RPM, 19,000 RPM, and stop in each between and take a sample and see what's happening. So not just go straight into the field weakening region, step by steps increasing the RPM and observe if you have any oscillations, because the field weakening is quite here you can see we have also some oscillations here, but not too much. So we have from 20 amp to 21.5 amp. We could decrease it if we do another encoder nonlinearity calibration at a different point, and you may observe better results, but these are pretty good, I guess. So these are not critical waveforms here at all. Okay, so until the end of this procedure, you have reached the maximum of the magnetic field weakening region, and you can make sure that your motor operates correctly also in MTPA region and also in the field weakening region, and you have validated it by ramping up slowly in different points and observing the plots and the operation. The last thing I would like to talk about is our inverter receives AC current vector targets, but you may need torque control, and we have a recommendation how you can reach that. This equation is basically the IPMSM torque equation, and from this equation we can express the lambda f, and from this we can calculate how much IQ current we need to reach that torque. And after using this equation and this equation, the IS is the total current of the vector length, and this IS can be sent directly via the CAN2 interface, and the lambda and the pole numbers and the ID and RQ are given values from the datasheet. And in this way, if you are using it in a quite fast loop, you are able to the big T is the torque. You are able to send a current command which includes your torque demand, and it can provide you the desired torque. This is a feed forward, so it means that you have to use the CAN2 feed from the CAN2 interface the ID actual current for that, but the rest of can be calculated and sent back to the inverter. So you do not need a PI current controller for this method. If you would like to have a very precise and accurate torque control, you have to do dynamometer test, because this torque relation depends on the LD and RQ, and this depends on the current. It depends on the lambda, the flux linkage, which is also temperature dependent, and other factors can imply the torque you request. So do some testing with that method and make sure it produces the right torque for you. And I guess that was all I would have liked to say about the motor control. There's a lots of factors, of course, but these were the most critical, which I think are very useful for troubleshooting, because when everything goes well, it's no questions, but when something is not working well, I guess these setup procedures helps you, this algorithm helps you to identify which point in your system you has any issues and help you to resolve that in time. So get back to Csaba, and let's start with the Q&A.
Yeah, so we had pretty much a lot of questions on the channel, but the vast majority of the questions have been answered, I think, with the team, the back office. We have highlighted some which maybe need some more elaboration or just a question. There was a question from Jens Haldrup that if the inverter uses a 900 volt switches inside because of the battery internal resistance and so on, if the region is high, it could induce the voltage slightly higher than the stated 120 volt max. The inverter is using 1200 volt SiC modules inside, so that's not the issue here. Where you should seek for issues, maybe potential issues, are the field weakening region. You should not let the system collapse the field during the operation and therefore boost the voltage as high as just virtually infinity. Then you should avoid this. Apart from that, the system is meant to be very robust and very safe with the 1200 volt switches, so I don't think that's an issue here. There was a question regarding if some thermal paste is necessary for the cooling interface. I think there is slight misconception here that we are just cleaning at this point. So here is a setup which we have made with the cooling and so on. So yeah, here you can see the motor which is theoretically assembled. Then you can use the whole surface of the motor as the thermal transfer area. We made a 3D cooling plate here. I think it's visible like here. There are like a spiral tube inside from somewhat, yeah, you can see it like this. And the end plates, like the ends of the interface is sealed with an O-ring. So all you need to do is just design in that way and make a slide with the motor like this, and the O-rings from at the end parts will seal the cooling. So theoretically what you are asking is right. So if you are planning to make your own cooling jacket in a mindset to increase the surface area of the motor, but from this way, you should use some thermal shrinkings or some thermal transfer paste. But this is like a more tricky way to carry this out. The more simple way is just to make a spiral tube like we made and seal it like this with O-rings. Okay, I think that's answered somewhat the question. Another question was if the teams need to use some tab washers for the DC connections. I have made some screenshots from other teams' solutions. We had a team from the Hungarian University Arabona Racing team that they have used this kind of tab washers. It's called DIN 463. You can easily check it on the internet. It's available off shelf, so you can just buy them and use them as is. So these are the way to make it like a rule compliant, and it's a pretty easy and straightforward way to make it happen. Okay, and one more question regarding what's the recommended way to measure the voltage at the inverter terminals without relying on the software and CAN data. So first of all, I will answer it shortly. The inverter shares the data via CAN bus, of course. You can read that. If you don't want to rely on that, you should somehow tap the DC plus minus anyways. I wouldn't recommend to do this on the inverter side to the joints of the inverter because the terminals are pretty close to each other. So I would avoid tapping the measurements at that point. I would seek somewhere else, maybe the solution, probably the fuses, the contactors, or something else maybe. But I wouldn't do that at the very point of the joint for the inverters. So yeah, that was the question list that I had from my end. So probably Richard has some questions as well. I don't exactly know.
Yeah, so let's say the first one. Will you support resolvers with a pole pair amount of more than 1 in the future? At the moment, we do not have a specific schedule for this. We support 3 types of resolvers, and 2 specified basically for this motor is the TE connectivity and the Heidenheim resolvers. If there will be more requests in the future from teams that they require more pole pair resolvers, we will consider it definitely, but at this moment I would say that we do not have a schedule for that. What protection does the inverter have to prevent permanent demagnetization during field weakening operation? For example, are there any limits on negative D-axis current or maximum field weakening duration? The inverter only gives the maximum amount of current specified by the motor current max parameter. It means if you send an AC current target, it will always be truncated to this number, and with setting up the system with this motor current max parameter basically acts a protection in the field weakening also, because for example you set 40 amp of current and you enter the field weakening region, and the current vector just laying on the D axis, you will end up such a situation where the ID almost not completely but almost will be very close or identical with the 40 amp of maximum. And if you set this motor parameter at a maximum current, you think that it will not demagnetize the motor, that it will also a protection, but we do not have any time frame for the magnetic field weakening range that how much time it can be in the magnetic field region. So basically that motor current max also apply to the negative D-axis current. Okay, calculating the torque is also applicable in field weakening and in MTPA region. Yes, this equation also works in MTPA and field weakening region because it has the ID current in the equation, and it will be more negative. Then the lambda will be a smaller value. Thus, you need more IQ current. That's more vector. So yes, it works in field weakening also. How does field weakening additionally affect motor losses? The field weakening is affecting copper losses, so ohmic losses. It means that also on the motor and also on the inverter is directly related with the current. No additional losses are there basically. So it's the same in the, so if you are controlling the motor 40 amps in the base speed and 40 amps on the field weakening region, from ohmic perspective, they are both the same on the motor and also the inverter. So that was all for my questions.
Yeah, so I think we have covered pretty much everything. I think that's the end of this session for now. The vast majority of the questions have been answered in the chat. I think the more tricky parts have been answered, which could be visual or more demonstrated could be answered here. So thank you very much for your time. And of course, this whole session will be available online after this event, so you can just check it back again. You can rewind it. You see the timestamps, and which might be interesting for your specific needs, and that's all. So thank you very much for your time, guys, and cheers.